Hello, I'm Katunja Brendan, your group 23. Uh, we are going to talk about we are working on the title of graph-based knowledge distillation for unsupervised East Coast Fever detection. Among our keywords is the graph attention mechanisms, machine learning, predictive modeling, graphical neural networks, knowledge distillation, and unsupervised learning. So we are going to start with the background and introduction. First of all, the East Coast Fever is a disease that attacks the cattle, mostly in eastern, central, and northern and southern Africa. It is caused by the protozoan and it is transmitted by the brown ticks and it is fed by the calf buffalo. Its impact is that there is high mortality rate uh, and also causes the economic losses for the farmers in case they lose their cattle. Among the symptoms is that there are swollen lymph nodes, there's fever, loss of appetite, loss or decline in the milk production, and also the loss in the meat production because the cattle literally becomes small. There's rapid breathing, nasal discharge, coughing, and abortion in the pregnant cows. Some of the challenges in the East Coast Fever ECF detection is that they used to use the traditional methods, which included the microscopic examinations, but then they were so costly and time consuming, so they were not favorable to the local farmers, and this would lead to more challenges because they were not able to detect it early. And also the farmers they face a difficulty in limited access to the advanced diagnostics. This also contributes to the loss of the cattle because they cannot afford, they are in the deep villages and they lack the services to provide and improve in their cattle farming. So among the solutions we come up with concerning machine learning is to develop a rapid and accurate ESF detection using clinical and environmental data. For example, we are using the dataset that has the longitudes and latitudes. It also has the temperatures among the clinical data. It has the genotypes, also the way the ticks are spread. The techniques that we are using, we have the graph attention mechanisms, knowledge distillation, graphical neural networks, supervised learning, and predictive modeling. The pipeline of machine learning is that we had first collect the data. For example, use the dataset from the website. We pre-processed it, and then we did feature engineering, which included the encoding to remove any entries that were actually not numerical because we are using a numerical dataset. But then we had, for example, in the genotypes, we have the 840K, so we had, and then the 54K, so we had to make it 0 or 1 because we are having only 2 genotypes. And also we did the exploited data analysis, which included the heat maps and the line graphs for different features. And also we did the machine learning pipeline for the ESF detection resistance. So we did some methodology here for data collection, the inputs of the cattle genotype, the farm location. I talked about the longitudes and latitudes, the tick exposure in the particular area, using the cell location, and also the previous infection data or history. We did the processing, which included data cleaning. I talked about it. The feature engineering that included normalization and encoding. So after that, we trained the models using one of these. Yeah, the model we deployed included the supervised learning, which included the clustering, included the knowledge distillation, included the teacher model and the student models, and also we did the recommendations after training the data. The model takes the new input and then computes the predicted infection risk percentage, and then generates the recommendation. Either the farmers, the veterinary doctors, the genetics, or the regional concerned authorities for the cattle in the particular area. So the related works or the recent trends in the literature review of the graphical attention mechanisms in disease modeling, multimodal data integration incorporates the diverse data for either imaging or non-imaging for particular comprehensive disease view. Here is an example of the Parkinson's disease. The gut model was used for the structure and the functional brain connectivity, which improves the prediction and also the enhanced interpretability. The guts help identify the key features in the disease protection. For example, in our dataset, the key features that we used were the genotypes, the tick exposures, and also the Cape Buffalo availability in the particular area. The application, our work is that the graph representation of the biological interactions was to construct a comprehensive graph of the genes, proteins, or the pathways related to the tick that spreads this this disease, which is the ESF. Then the multimodal data integration, it combines the genomic and then the clinical data for the historical view of the disease dynamics and the improved prediction of the insights. So talk about the problem statement. As I mentioned, that the cattle farmers in Uganda face a challenge of identifying the potential outbreak or infection of the East Coast fever, as it is very essential for management and treating of this disease, as when it is detected late, cannot be cured, however much effort is put in. The computational problem is that it is possible to predict the East Coast fever in cattle, but there are several challenges that hinder the effective application of a machine learning model. And this project, which include the data used to train the model, may not be consistent and accurate, which affects the accuracy of the model. For example, the data we used was the data set we got was imbalanced, so it included the balancing of the data model. But then during the balancing, some of the fields were removed to actually make sure that this data is balanced and we avoid the bias of the model. So this reduces the data set and also makes the data set smaller, which reduces the accuracy of the trained model on this data set. And also another challenge is that the knowledge distillation we used here, we use it to create a lightweight model, for example, in our deployment. But then this student model we deploy is actually less accurate than the student model, which also reduces the accuracy and the efficiency of this deployed machine learning model. The research questions and then the objectives of this work is to improve the performance and early detection of ESF using the graphical attention mechanisms. But this helps to the question may be that what it helps to solve is that it enhances the early detection through the modeling and the complex relationships in the data, as it is very essential. And also to build a low-cost but high-speed ESF detection system through knowledge distillation. This solves is that it allows the right models that can work in real time and on premises while we expect this outbreak, and also access the graphical neural networks performance in inferring ESF transmission probabilities and with failure patterns. About what this solves is that it identifies individual cows at risks and in their tracking history. Another one is examine the potential of unsupervised learning in the detection of ESF clusters and outliers in unlabeled data. To talk about the research contributions, is that we deployed a hybrid machine learning model that combines the unsupervised learning, KMeans clustering, and also the unsupervised learning that uses graphical convolutional networks to address the challenge of farm risk classification. And also, we built a fast knowledge distillation framework for farm risk classification, where a smaller, efficient student model learns from a larger teacher model for high performing. And also, we deployed a novel graphical-based approach to model the spatial relationships between farms using the graphical convolutional networks, and introduced a robust data processing pipeline that incorporates smart or synthetic minority oversampling technique under the class imbalance. To talk about the methodology, is that at first we have the dataset, which includes the cattle genotype, environmental data, which included the temperature, tick exposure, and Cape buffaloes, and also the geographical data that included the farm locations, for example, the longitudes and latitudes, and also the cattle density in the particular area. We moved on to the data processing, pre-processing, which includes the data cleaning and normalization. Also included the feature engineering, encoding, and scaling. Encoding included the making the non-numerical fields numerical, and also the graph construction. For example, we had to do the cattle and farm network, and also we had to come up with the nodes in the features since we are using graph attention mechanisms. Then we moved on to model training and learning. The graphical neural networks was used as part of this, without forgetting unsupervised learning, which included the clustering and autoencoders, and also the traditional machine learning, which included the random forest decision trees, and also the DX-Boost. About all this above, we did the knowledge distillation, which included the teacher model, the student model, and also we deployed, we use this predict and also deploy, have the infection risk prediction, and also these risk-based recommendations were deployed through the using the first API, which we used the Streamlight Cloud to deploy the Booster UI, and then the first API provided these predictions. These can be used by the farmers, the veterinary doctor, the geneticists, or the policymakers. The farmers can use this deployment tool, this deployed tool for high risk cattle alerts, and also the veterinarian can use this deployed model for disease control. The genetics can use it for selective breeding, and also the policymakers can use this model for regional disease control strategies. Thank you. Allow me invite my colleague to start from here.
Good evening. My name is Benham Shadek, and I'm here to continue from where my colleague has stopped. So, if I talk about the output or expected results and discussions, we have a variety of results we extracted from the models we created. Then we can first talk about these results which are before us, which are for the hybrid model, which implements unsupervised learning plus C, supervised learning, and in addition with knowledge distillation. So if we are to see the first graph, which talks about the learning rate over the epochs and the loss over the epochs, then the farm risk clustering for the student GNN embeddings, and then the student model matrix, then the student model confusion matrix, then the teacher evaluation results. We can see clearly that the model is really performing well, with the accuracy close to for the teacher model close to 88.46, the precision the same, the recall which is 88.46, and the F1 score which is 88.45, and the teacher model performing slightly lower but with still much better accuracy, precision, recall, and F1 score. Then next we can talk about the expected results for the results for the hybrid model, but this one only implements unsupervised learning plus supervised learning without knowledge distillation, and this one clusters using the KMeans clustering. It classifies or it categorizes the farms under 3 clusters: 0, which will represent the low, which will represent low risk; 1, which will represent 1 will represent medium moderate risk, then 2 will represent high risk. And according to what you see here, this model also performed literally well with an accuracy of 86.54, which is not bad. Then the next one is for unsupervised learning, where we applied the Graph-Convolutional Networks plus clustering, and these are the results. That's the accuracy based on the training and the testing data, and that's our test set confusion matrix, F1 score. And if we see here, a model literally didn't perform bad with an accuracy of 65, and the macro average and the weighted average almost the same. So yeah, this is also another model. Yes, briefly, if I talk about it, yeah, it also literally performed well with an accuracy of 72.7, which is not bad. And these graphs portray the learning rate, the training loss, the farm risk clustering, the model evaluation matrix. Yeah. So next we can talk about the conclusions and limitations, where in a conclusion we developed a hybrid model that combines unsupervised learning, KMeans clustering with supervised learning using Graph-Convolutional Networks enhanced by knowledge distillation. And the key accomplishments include increased accuracy, improved efficiency through a lightweight student model, and enhanced interpretability through clustering and visualization. However, there are limitations. First, capturing accurate relationships between the farms for disease transmission is really challenging. And then second, the model's performance is sensitive to hyperparameters like cluster count and graph-convolutional network layers. Third, there is a high computational overhead during training, especially for large datasets. And finally, while simple minority SMOTE helps with class imbalance, it may create synthetic data that doesn't reflect the true minority class distribution, risking overfitting. Yes, so we can talk about the next steps. So looking ahead, our future work will focus on enhancing graph construction, merging external information like weather and soil quality, and increasing scalability and interpretability of the model. And this model contributes to agricultural risk management, paving the way for sustainable and resilient farming systems. Lastly, we shall talk about the acknowledgements. And we would like to extend our gratitude to Dryad Digital Repository for providing unrestricted access to the dataset which we used for the development of our model. And we also like to thank the original authors of the dataset for their efforts in the data collection. Their contributions have been really invaluable and in advancing our study of machine learning based prediction of East Coast fever in cattle. So that's all from me. Thank you.